Welcome to lecture 14 of Machine Learning from Data. And this is one of my favorite lectures of the course because we're going to sit back and we're going to take stock of all the theory that we have built, all the foundations that we have built up to now. It's not going to be a very mathematical lecture, but we're going to condense those foundations into three very important learning principles. Okay? And whenever you approach a machine learning problem, you want to stick to these principles like glue. Now, before we get going, let's talk about what we did last time. So we talked about validation. So we're constantly after this link from the in-sample to the out-of-sample, in particular the out-of-sample error. And the VC theory gave us this error bar that links E in to E out. Validation gives another estimate of the out-of-sample error. It directly attempts to estimate the out-of-sample error. And, the basic idea is quite simple. In the standard setup, you take your data set and you learn and you produce a final hypothesis G. Now, behind closed doors, here's what you do. You take that same data, okay, you split it randomly into a training set and a validation set of size k. From the training set, which is deficient sum data, you produce a deficient hypothesis G minus, and you evaluate that hypothesis on your validation set, outputting the validation error as your estimate of the out-of-sample error for G. Now, is that a good estimate? Well, it depends. Okay. If k is too large, so actually the validation error is an estimate of the out-of-sample error of G minus. So you'd like k to be large for that estimate to be accurate. But then if k is large, there's a big deficiency between G minus and G. Okay. So how do we get over this? That's cross-validation. It's the queen of validation. And if you can computationally afford to do it, that's the guy you go for. Okay. Cross-validation allows us to essentially do validation with a k of 1. So you only sacrifice one data point in the training set, but then average over all possible choices of that one data point. So you output the cross-validation error, which is in some sense the estimate of the out-of-sample performance when you learn on n-1 data points, and you output that as the out-of-sample error for G. Now, now we have two sort of ways to estimate the out-of-sample error. One is the VC error bar added on to the in-sample error, which gives us a bound. And the other is the cross-validation estimate ECV. And if your hypothesis set starts out as relatively simple, then the VC error bar usually wins, or it might win. But very often in practice, the cross-validation estimate beats the upper bound because it actually goes after an estimate of the actual out-of-sample error. Now, one of the most important uses of validation is model selection. You have a bunch of models. They produce, you can think of them as finalist hypotheses. And how do you pick one? You can use validation. If you've held out a validation set, you can use validation to pick one. Okay? Very useful for a supervisor who has a bunch of minions who are all going at it with the data. The supervisor doesn't need to know what they did. They just produce their final hypotheses, their finalists, so to speak, and then the supervisor can select. Okay, so that's validation. What's going on today? Today we're going to talk about these three important principles, and they address the three parts of the machine learning problem. So what do you do before you see the data? You have to pick your hypothesis set. You have to pick your model. And we're going to study Occams Razor in this context, which basically says pick your model carefully. Okay? Now, after you've picked your model, before you see the data, now you need to go and get the data. So, how do you get the data? You have to get your data carefully. Okay? And sampling bias is one of the pitfalls that many machine learning applications fall into. And so we'll address sampling bias. Okay? And then, after you've now gotten your data, you need to use your data. You need to handle your data carefully. And again, one of the pitfalls that of many applications of machine learning fall into is data snooping. So we'll discuss data snooping. So we'll discuss Occam's Razor, sampling bias, and data snooping. Okay, so let's talk about Occam's Razor. And the quote below is generally attributed to William of Occam. And here's what he says. You should trim down any explanation of the data to make it as simple as possible, but no simpler. Okay, now let's take this in the context of scientific disciplines. So the data is golden. So whatever theory you have has to explain the data. But there may be many theories that can explain the data. And so what Occam is suggesting is that, you should pick the simplest that explains the data. Now, what about the explanations that do not explain the data? Well, you can throw those out. Because, in the scientific disciplines, the data is golden, and any correct theory must explain all the data. Okay? And in the machine learning context, let's put it into a nice principle that we can box. Okay? Basically, what Occam is saying is the simplest model that fits the data is also the most plausible, is the better model. Okay? And I've highlighted, the simplest model, and I've highlighted most plausible. So basically, by most plausible, we mean better, not most beautiful, not the one we like, and we're not talking about some aesthetic, plausibility. We have a very concrete, sort of definition of what's better, and we are thinking about the out-of-sample error. Okay. Now let's nail down, the simplest model. What does that mean? And let's nail down the most plausible. What does that sort of mean? And if we were to operationalize this principle, okay, basically what we're saying is beware of complex models that fit the data. Okay, so now let's nail down, simplest and plausible, and then let's look at a couple of examples. Okay. So what does simpler mean? Now, we've actually seen simple in two contexts up to now. The first is, when we studied regularization, we talked about simple hypotheses. So we introduced this complexity penalty, omega of h, for a hypothesis. And in various disciplines, the notion of a simple hypothesis has, cropped up in many shapes and forms. Okay, so we have this complexity penalty for a hypothesis. You can think about low-order polynomials. You can think about hypotheses with, small weights. You can think about easily described hypotheses. Okay. And that's a very computational sort of definition of a simple hypothesis. Now that we have computers, Turing machines basically, now that we have computers, we can think of the complexity of a hypothesis as being quantified by the length of the shortest program that can compute that hypothesis on an arbitrary input. So there's a hypothesis h of x, you're going to give it an arbitrary input x, okay? And now you're expecting to see h of x come out, and there's a box, which we can call a computer or a program, and the shortest program that can faithfully compute h of x, you could quantify the complexity of a hypothesis by that length of that shortest program. Okay, so there's this notion of the simplicity of a hypothesis, and then when we study the VC theory, there's this notion of the simplicity of the hypothesis set. Okay, so we had this, VC penalty, omega of h. Okay, this guy omega of h, the complexity penalty error bar that links E into E out, and that essentially is an error bar that quantifies the complexity of your hypothesis set. So simpler hypothesis sets have, a small VC dimension, or if they're finite, a small number of hypotheses. And in electrical engineering and other areas like, physics, we can quantify the complexity of a set by its entropy, and so on and so forth. So there are different ways to quantify the simplicity or complexity of a hypothesis, and there are different ways to quantify the complexity or the simplicity of a hypothesis set. So on the one hand, you have an object. On the other hand, you have a set of objects. And these two are linked. And there's a fundamental link, okay, that, if you have a hypothesis set with simple hypotheses, it must be a simple hypothesis set. It must be a small hypothesis set. And we can sort of easily see that link if we look at, hypotheses that are easily described a la programs, okay. So if you have a hypothesis set with simple hypotheses, then it means that hypothesis set is only containing hypotheses that can be implemented by short programs, but there are way fewer short programs than long programs. So, by just a counting argument, the hypothesis set has to be small. So simple hypotheses, if those are the only ones in your hypothesis set, then it must be small, and so the hypothesis set itself is small. So there's a link between these two. And we had a glimpse of this link when we studied, regularization, where we started with the soft order constraint, which is this constraint on H, so it constructs a smaller hypothesis set. Okay, and then we did math and this and that and this and that, and we gradually reduced, learning within a smaller hypothesis set to being equivalent to learning with a penalized error, the augmented error, where you penalize the complexity of a hypothesis. Okay, and so there's an equivalence there, and we saw that equivalence, in a way when we studied regularization. Okay, so that's what simpler means. So we have to, so in essence, even though we might think that there are multiple, appearances of simplicity in our context, simple hypothesis versus simple hypothesis set, they're essentially the same. Okay, and they're quantified by, for example, omega of h or the VC dimension or what have you. Okay, so that's what we mean by simpler, and simpler is better. Okay, so why is simpler better? Okay, and now I'm gonna take you back to my childhood. I used to love reading Conan Doyle's Sherlock Holmes stories. Okay, and I'm in gray here. I've highlighted one of an excerpt from a story. Now, Detective Gregory is the typical detective who is a bumbling detective, doesn't know what's going on, and he asks Sherlock, is there any point to which you wish to draw my attention? Okay. And then Sherlock says, to the curious incident of the dog in the nighttime. Okay, and then you're thinking, okay, and as the bumbling detective is thinking, the dog did nothing in the nighttime, so why are you pointing my attention to this dog doing nothing and calling it a curious incident? And that's exactly what Sherlock says. He says, that was the curious incident. Okay, so now let's think about this. Okay, so the detective is bumbling around, looking at clues here, looking at clues there, and so on and so forth. And Sherlock Holmes is sitting here looking at the dog and wondering, why didn't it bark in the nighttime? Okay, now there's a crime that has been committed, and no one heard the dog bark. Okay, and that is very surprising. Okay, that the dog did not bark, because if a stranger comes and commits a crime, you expect the dog to bark. Okay, and the fact that the dog did not bark is very surprising. And therein lies its significance. So okay, if I continue the story, the conclusion is, well, the dog not barking is a very significant observation, which the bumbling detective, missed, but obviously nothing escapes Sherlock Holmes. Okay, and Sherlock Holmes said, well, that's a very significant thing, because the likely thing, is for the dog to bark, and the unlikely thing happened, and so that's very significant. Okay, and then the detective finally gets it, that, that means that, whoever committed this crime was not a stranger to the dog. Okay, because typically crimes are committed by strangers, the dog would have barked. Okay, and what's the moral of this story? Okay. When something unlikely happens, if you get surprised, something significant has happened. Okay. Now let's take this to the context of learning, and why is simpler better? So you have a simple hypothesis set. You're approaching a big data set, let's say 100 data points. Well, when we say simple hypothesis set, we're usually talking about simple with respect to the number of data points you're going to see. So you have a simple hypothesis set, you're approaching 100, 200, 1,000, 1,000,000 data points. And what are you expecting? You are expecting to utterly and miserably fail. You're expecting an in-sample error close to 0.5 if you're doing classification. Okay, and that's because you have a simple hypothesis set. But what a surprise if your simple hypothesis set can fit the data. Something very unlikely has happened. You are truly surprised. It's very significant. It's very significant now if, expecting to fail, you succeed. Okay? Something is going on. Something interesting is going on. Okay? And so that's sort of, in a parable, why simpler is better. Because simpler is better because when you fit the data, you are more surprised. And let me show you that, in a very simple setting, that'll sort of make the point very striking. Okay, so let's consider a scientific experiment. Okay, now, there's this physical theory, and we postulate that, the resistivity of a metal is linear in the temperature T. So that's the physical theory postulates this. Okay, so we send out our scientists to investigate, and scientist 3 comes back, and has collected, the resistivity with very, very careful measurements, has collected the resistivity for 3 temperatures, and, finds that, okay, so they're almost on a line. Okay, there's this red guy who seems to be an anomaly, or is it an anomaly, or have I falsified the theory, or what have you, who knows. Okay, so scientist 3 comes back with this data, and, say, okay, thank you very much. Okay, and scientist 2, comes back with this data. Wow! Okay, unbelievable. Scientist 2 has come back with this data, and scientist 1 comes back with this data. Okay, so has collected this data, and also looks like scientist 2 has managed to fit a line to his or her data. Okay. And the basic question we're going to ask is, which of these scientists have provided the most evidence for the hypothesis resistivity rho is linear in temperature T? Okay, so pause the video, okay, and think about this question. And, rank the scientists in order of who has supported this theory the most. When I say the most, I mean, most, then second most, and then third most, and then we will discuss. So pause the video, 1, 2, 3 seconds. Okay, now, if you're coming back, and you just want to hear the discussion, here we go. Let's compare scientist 2 with scientist 3. Okay, so that's our first, attempt at analyzing this sort of, these scientists. Okay, so scientist 2 has provided, in my opinion, very convincing, evidence. Because look, he has collected 3 data points, and, a line beautifully fits those 3 data points. Scientist 3, on the other hand, you might say, well, scientist 3 has, in some sense, what we call scientist 3 is a falsifier. Scientist 3 has falsified the hypothesis under the assumption that the data is exact. And we all know that when you do these physics experiments, there's measurement error and so on and so forth. So if we allow scientist 3 a little bit of slack, because there's some error, there could be some errors in measurement and so on, well then scientist 3 has provided some evidence. Some evidence, because we know that measurements cannot be exact. And in fact, having said that, we might go back to scientist 2 and fire scientist 2. because I'm starting to suspect that scientist 2 has falsified the data. Because, I mean, how is it possible? There's measurement errors and this and that, and he's got 3 data points that lie exactly on a line. Okay, whatever. Okay, I'm starting to suspect scientist 2, but assuming that everything is above board, scientist 2 has given us basically very convincing evidence for the linearity, but scientist 3, if there's noise in the data, it's pretty decent evidence. Okay, now let's compare scientist 1 with scientist 3. So we all agree maybe that scientist 2 has just given us golden data, golden evidence for this theory. Okay, but now let's consider scientist 1 versus scientist 3. Well, we might argue as follows. Scientist 3 has said the theory is wrong, although if we allow noise, some evidence. What about scientist 1? Okay, that's the interesting guy. Okay, and I claim that scientist 1 has given us no evidence for the theory. And I don't mean, like scientist 3, has maybe given us some evidence, okay, depending on how much noise is in the data. Scientist 1, on the other hand, no evidence. Zero, flat zero. Okay. And, we all know that you collect any 2 data points, you can send a line through it. Okay. So, this doesn't provide any evidence at all whatsoever that resistivity is linear in temperature. Resistivity could be exponential in temperature. And scientist 1 who collected 2 data points would still be able to send a line through his 2 data points. Okay. So let's try to pin down in exactly what way is scientist 1, giving us no evidence. Scientist 2, of course, we all agree is the best evidence. But I would take scientist 3's data over scientist 1. Scientist 2 is perfect. Scientist 3's data at least gives some evidence. Scientist 1 gives no evidence. Now, let's look at it from the point of view of the surprise factor. Okay. In scientist 2's case, both scientist 2 and scientist 3 are collecting 3 data points. And when the line, which is a simple model, fits the 3 data points, man, are we surprised. Wow. Very unlikely to happen. It happened. Okay. We are so surprised. It's significant that it happened. Scientist 3, we're expecting a total, mess, and he almost fits the data. So we're pretty surprised. Significant. Scientist 1, we're not surprised at all. There's no surprise factor. There's no wow factor in what scientist 1 did. Okay. So, no evidence. It's not significant at all. Okay. Now, we can sort of summarize this in what's called the axiom of nonfalsifiability. Okay. And let me tell you, this is a fundamental axiom. Okay. It's a fundamental axiom in the physical sciences, and it basically goes like this. You have a hypothesis, okay, and you'd like to, run an experiment to test your hypothesis. Okay. It must be the case that your experiment has a chance to falsify your hypothesis for it to be worth running the experiment at all. In other words, if your experiment has no chance of falsifying your hypothesis, then the experiment provides no evidence one way or the other for the hypothesis. It cannot, it cannot say the hypothesis is false. It cannot say the hypothesis is true. Now, scientist 2, when collecting 3 data points, could have been falsified. The fact that scientist 2 was not falsified is meaningful. Scientist 1 could not be falsified because there's no way to collect 2 data points that can falsify the linear hypothesis. So, scientist 1 could not be falsified. No point doing this experiment. Someone should have just told scientist 1, don't waste your time collecting 2 data points. It's of no help whatsoever. Cannot say that the theory is true. Cannot say that the theory is false. Principle, the axiom of non-falsifiability. If you cannot falsify your hypothesis, okay, then don't waste your time running the experiment. Now, how does this come into machine learning? Okay, so falsification plays a fundamental role in this notion of why simple better, and let's go back to now our good old friend, the growth function. Okay, and let's consider a hypothesis set H that shatters a data set x1 to xn. So you've got a data set x1 to xn, and H shatters. Now you can generate your y values, because that's what you do when you collect the data. You have your x values, and then the target function runs and gives you examples of f in action. So you get your x1, y1, x2, yn, and so on. Okay. But if your hypothesis set shatters the data, now here's a little exercise for you to prove. Okay. No matter what y values you put there, you can get in-sample error 0. So don't be surprised if you fit the data when your hypothesis set is complex enough to shatter the data. Okay? Don't be surprised. And if it's not surprising at all, then it's not significant at all. Let's reformulate it a little bit more concretely. If your hypothesis set shatters the data set x1 to xn, then the experiment of collecting the y values is pointless, because you can think of the following hypothesis. You can think of the following sort of claim that you're trying to verify. The hypothesis set H is a good set of candidate hypotheses for F. So think of that as what you're trying to verify by going and collecting the data. Now, when you collect the data and you see that some member of your hypothesis set fits the data well, you conclude, wow, yes, my hypothesis set is a good set of candidate hypotheses for F. And what's my evidence? Look, I fit the data. But if your data is shattered by your hypothesis set, don't waste your time. Okay? Because you can't falsify that claim that the hypothesis set is a good set of candidate hypotheses for F. In order for the experiment to be worth running, it must be the case that you can falsify the claim. Now let's look at the other situation. H doesn't shatter your data x1 to xn. In fact, we could even make a stronger statement. H cannot shatter any data set of size n, so the growth function is small. Okay, then if you imagine that the target values are generated randomly, then the probability, the number of dichotomies H can implement is m sub h of n at most. Okay. So the probability that it will be able to implement whatever dichotomy is generated, if you generate randomly, is m sub h of n divided by 2 to the n, because you're going to generate each of the dichotomies randomly. So the probability that your hypothesis set is falsified is 1 minus of m sub h of n divided by 2 to the n at least, because m sub h of n is the maximum number of dichotomies, not necessarily the number of dichotomies on your data set x1 to xn. Okay, so if m sub h of n is polynomial, then you see this term, this m sub h of n divided by 2 to the n is minute. So the probability to be falsified is almost 1. Now imagine your surprise when you go and run the experiment, generate the y values and try to fit, and you find that you fit the data extremely well. You didn't, for example, got in-sample error 0. You didn't get falsified. It's a very surprising outcome. It's a very significant outcome. So a good fit is surprising with a simpler H, and hence it is more significant. You could have falsified your hypothesis set. You could have falsified the claim that H is a good set of candidate hypotheses for F, but you didn't. And the fact that you didn't is significant. Okay. So that's how simpler is better sort of enters, and that's where the theory put a sort of a quantifiable notion of better on learning. Okay, so simpler is quantifiably better because you get this smaller error bar. But intuitively, it's because the hypothesis set can be falsified easily by the data, and when it doesn't falsify, it's significant. Okay, now I'll read you a quote from the textbook. Okay, because there's a slight difference between Occam's principle for the sciences and Occam's principle for machine learning from data. And what is that fundamental difference? The fundamental difference is that in the Occam world, in the scientific world, a theory either explains all the data or it's wrong. Okay? So we're not interested when we talk about theories for physics about theories that explain some of the data. Even if there's one data point that the theory cannot explain, you throw it out and you need to look for another theory. Now, machine learning is slightly different because our goal is to predict as much as we can, as well as we can. Our goal is to get the out-of-sample error small. Okay? And so, in order to get the out-of-sample error small, it's not necessarily the case that we must get in-sample error 0. Okay? And so let me read the quote. We may opt for a simpler fit than possible. Okay? So we may go even simpler than what Occam says. Occam says, go as simple as you can, providing you fit the data. But we may go even more simpler. Okay? Namely, we will go for an imperfect fit of the data using a simple model over a perfect fit of the data using a more complex model. Okay? And the reason is that the price we pay for the perfect fit, so in order to get that extra bit of in-sample error down to 0, the price we pay in terms of model complexity, okay, the price we pay in terms of the penalty for model complexity may be too much in comparison to the benefit of the better fit. Okay. So the machine learning has taken Occam's Razor sort of a step further and says we can tolerate larger in-sample error. Okay? And so there's this trade-off. It's not that we go for the simplest fit that explains all the data, because you may have to go to too complex a model, especially if there's noise. Okay? So we'll go, we can quantify the trade-off between the in-sample fit and then the out-of-sample, the complexity of the hypothesis set, and the sum of these is what we optimize. So we go a step further than Occam. We can actually trade off the two. Occam says you can't trade off the in-sample error. That must be zero. So now get the simplest hypothesis that accomplishes. In machine learning, we can trade off. So we can go for in-sample error slightly bigger than zero, because otherwise we pay too huge a penalty in complexity. Okay, now let me show you an example from the real world, just a fun example. Okay, you can think of it as a puzzle.